Welcome to a new test and teardown video. Today we're going to look at the Kunkin KP184. It's an electronic DC load and it's quite cheap. It's still available on different online shops. At the moment it's $185 and shipment is another $57. So yeah, this is a current product you can go and buy. Its specification is quite straightforward. It's written here, 150 volt or 40 amps, and the total is 400 watts. I don't know if this is really true, because if you look at the manual, we got two different loads. We got the KP184 and we also got a 182, and that one should be a 200 watts. And the 200 watt variant is 3.4 kilos or something like that according to the manual. And the KP184, this one, the 400 one, should be 4.5 kilograms, but this one is 3.4 kilograms. So what is wrong here? I think maybe there's a little bit of missing heatsink, so maybe this one is not the correct version, or they have tricked something, or they have upgraded the heatsinks, or whatever they have done. I can't wait to play with that one. But first I want to show you a little bit of funny things. Oh, it's better to have it here and there. So at the moment I got about 20 volts input. I have adjusted the voltage up a little bit. And if I turn on the load, I just give it 1 amps to start with. See something funny. Let's turn off mains input. It's the same as activating the switch on the behind, but it's just easier for me to use my little remote test here. So now we turn it on again, and what do you know? It goes on again. So what you think is that, oh, it's maybe remembering my settings and stuff like that. Let's turn it off. And we still have it set for 1 amp, obviously, right? And current mode and all that kind of stuff. So let's turn off the mains and then turn it on again. Now you would expect it to go off, right? And remember the off setting, but it actually goes to load mode at power on. I think it's not a big problem, but I really want you to know that this is what it is doing. Depending on whatever you're doing, of course, you turn this on first, adjust whatever settings you want, and then you apply your input. There's an about applying input. There's something I really want you to know first of all, and that is the banana plugs. Obviously, this thing can do 40 amps. So of course you're not using banana plugs. So it really isn't a problem. But if you want to load 1 amp or whatever, you see, I don't know if it's that evident here, but those bananas that I'm using here, they handle, they're very, very springy, so they handle a very big loose hole as well as the correct diameter. This hole here is way too big compared to a normal banana plug. So of course, if you got really, really good connectors like I got here, it is not a big problem. But if we take a more crappy one, like this type here, yes, it's gonna go. That was a bad example because that one was actually not as crappy as I wanted. Perhaps I only got. Oh yeah, this one. Uy, 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 uy. That is loosey juicy. Can you see that? There's no. There's just no grip at all. I mean, that is absolutely useless. What have they done? But of course, you want to screw these out and use the correct method, right? So let's just try and load this thing and see what's happening, right? I wanted to test both of its current and voltage ranges just to see what happens. So here is my little baby. It's a power supply that can easily do much more than this. So let's just try and see what happens here. So how we're going to change the current set, because we are in constant current mode. Let's go out of this. If we are in the mode, we can change the different modes. So I go off, and then we click the different modes. It's easily indicated with an LED under the text here. So obviously this is not a super modern top sexy load with LED TFT screens and all that kind of stuff. This is a 7-segment screen and just some LEDs behind some text. So obviously you need to be a little bit with imagination, especially when it comes to configurations and settings and all that. It is a little bit difficult, and of course also when you look at the quality of the manual, it is a little bit limited. So I mean, yeah, it is could be a little IQ test for some of you guys. I mean, I had my problems with some of the details in the manual. Anyway, set, because we're in constant current mode, it will go straight to current, and you can use the arrows here and crank up the amps like that. There are a few things in the manual that is wrong. For example, they say you can push the knob. So I would expect in the older versions or previous versions, they would have a button here, a push button function on the dial that is probably connected in parallel with set. So now we have set the 11 amps, and then we can crank it on, and then we'll get the 11 amps. So, but it is not available in the model I got here. So what we want to do is we want to play with set, and we want to see what happens. This is live, right? So what happens if we, oopsie doopsie, big shockity shock, 40 amps on. And why is this not working? Why are you doing this to me? So is it too much for you? Okay, so it can... there's a software limit for current. It's full of all those annoying software limits. So this one is of course at a 40 amp current limit. Haha. So you can of course do 39.9. That is so stupid. A 40 amp load cannot do 40 amps. I mean, yes, and funny is that. So maybe we should try and test the voltage. So here's what we do. I always set up stuff first, because there's a potential of this one could output much more than my load here can handle. So this is why I do it that way. Let's see what happens. Sparkity spark. And then I should be able to hit the on 0.5. It goes a little bit unstable. Perhaps it has something to do with those are a little bit loose here. I'm not happy. It could also be due to the capacitor issue. There is a known capacitor issue with this load. And that is also what we want to inspect. Ooh, we're loading it too much. How about 6.9? Can we do that? Ooh, we're too close. Oh, look at that. And there's a lot of ripple and problems. And I have not seen this before with any of the other loads or any of the other experiments I've used this power supply for. So this one is a little bit funny, this ripple thing. So I think it is time to open this load, and let's have a look if it got this funny problem. So let's look a little bit on the back before I open it. We got the normal RS232 serial port, and you can connect this to all sorts of test software, of course their own, but it's also included in Test Controller. So, and that is a free software you can download and simply just pick this unit and then you can remote it. We also got the 485. Yes, here's an for external trigger plus 12-volt pass fail, and I believe the last two that will be for remote sensing. And a big fan, of course. And this is where they hit the on-off switch and mains voltage selector. Inside this wonderful Kunkin DC load. It is really not that bad at all. So we've got 3 field effect transistors here on the top as current sources. We got some op amps and drive and stuff like that, 4 of them. Here is an STM32 microcontroller that's doing all the brainiac. And the interfaces, they're all optically isolated with the optocouplers. Here's a little isolated converter for a supply of all the stuff like that. So really a good way to avoid a current loop. So I kind of like that. We got a little bit of resistors standing up like that. It's a little bit weird because everything else is SMD. Okay, that will be individual source resistors for current sharing of the 3 field effect transistors here. We got 3 more at the bottom here, and this is a very, very effective way to heat sink stuff with a big and powerful fan. And we got a temperature sensor and a fan control system. Mains transformer, quite a lot of secondary windings. We also got the 2 blue in there. All those secondary windings, they go to these 2 connectors. We got a bridge rectifier and 4 individual diodes as another rectifier. Isn't that a little bit funny? I can't help it. That is funny. Why would you not use the same kind of diodes? But yeah, that is what they do. And that is the fan connector. And yeah, here's the temperature sensor in the middle of the heatsink. They just glued it using silicone glue. Well, that's also a little bit funny. I don't know yet what the relay is doing. Oh yeah, there's another little funny thing. What they have done is input goes via those 2 cables here. So that is 40 amps capable cables. So they're probably superconducting, as you can imagine. I think they're a little bit too thin for the 40 amps, but and look at those tiny little. But that is our 40 amp input, and of course we got sense using the sense wires here. Very close to the input of the 40 amps to the top board, we got another cable that is soldered in just behind. On the bottom here, there's a hole where the wire goes down to the bottom board with another 3 field effect transistors. And let me show you how they've done this. As you can see here, most of the copper is inside the hole. I don't know if you can see this. We got a little bit of loose ends sticking out to all the sides and stuff, on both of them actually. So that's a little bit funny. Why don't they twist them carefully enough, pre-solder and then stick them in? And then the wires goes to the bottom board. And again, 3 field effect transistors and a source resistor for each of them. And that will be the main current sense resistor, that one here. And it is, of course, placed directly into the air intake. So that one you want to keep as cold as possible, but you also want it to be at a constant temperature so that your current settings will be as accurate as possible. And I don't know if you can see the the wires here, but that is now only 20 amps in those wires. But you can see they almost solder it. I mean, see? That wire, I would recommend the wire to go all the way through and then plenty of solder on both sides. I mean, what do you call this? Barely soldered. Yeah, okay. But that is how it is. And that is the bottom PCB for the 3 field effect transistors. They got, of course, local op amps to do the local current control. And I would definitely imagine that the different ranges of current, of course, if you are in very low current range, you would, of course, only turn on one of the 6 current sources. That will make most sense, and that will give you the highest possible resolution for current. There's another little manufacturing smartiness that I've done here. So look at that, the blue PCB here on the bottom for mains entry, voltage selection, and on-off switch, all in one little PCB. That means you cannot do this wrong. Stick in the board, solder, job done, and it's gonna work all the time. So that's quite nice. So this tiny little mains input transformer is, of course, plenty to handle all this. This unit uses about 10 watts from the mains supply. So this is the rear side. And this is the resistor everybody talks about, is easy to find, R10. And the capacitor you're suggested to remove is this one that is just below R10. Maybe that is called C58. That could be the way that it is done, right? And somebody also talked about later versions of this load. The capacitor is mounted again. They also saw this capacitor removed from factory, and they saw it mounted again, and then it is now 10 nano, and originally it was 100. So what I want to do is, I don't know the versions or the numbers or the year codes or any kind of things about this unit. So when was this done or not done? So remember the instability in the current that we played with? So it could be that is what I need to do. So what I want to do is remove it and measure its value. So I believe my capacitor is about 10 nanofarad, and this should be an 805 size, right? Haha, look at that. I'm sorry about the multiplexing here. On a video it goes absolutely berserk. Oh, okay. Now it is safe, but weirdo. But it is a lot more stable now compared to before. So definitely we want this capacitor to be removed. Okay, great. At least we know it was 10 nanofarad and now it is gone. Here is a little high-speed clip that shows the flickering of the display updates. It's of course because the displays, they are multiplexed. So one of them is on at the same time at the top, middle and bottom rows, and then they multiplex like you see here. And this is why it flickers on my video. I can also say that it has something to do with the voltage. Now I went down to 100 and then down to 50, and the lower the voltage, the more nice and stable is the current. And of course they're real smart. They have filtered the readout on their unit here so you don't see any jitter or anything funky going on. You just see your set point. And this is of course the real current. Just to show you, it's not my power supply that is broken. I just use another DC load. And then this is the readout jitter we have on this power supply, and this is the set point of the current. So that is quite all right. I just double checked that capacitor value on the EE block forums. Originally it was 100 nano, and then people removed it, and then Kunkin, they put in 10 nanofarad originally, or in the next batch, right? So this one was 10 nano, as it was supposed to be from the factory. However, now I have removed it, and there's clearly a big improvement of this stability problem. So I think I will update to the EEV block about my findings, and probably this is going to help some other users of this power supply. Definitely so far I didn't see any negative side effects, so 0 is what we want here. So this is the display board, and that will be all the 7-segment LED displays. They're soldered into all this. I don't know what you call this kind of solder job here, with little pieces of metal parts. Can you see all this little metal here? And it's just all over the place, because first of all they didn't really solder it that beautifully, and they didn't clean it either. Well, this is what you get. So now the display unit here is removed. That was quite easy. Just lift out a little bit here, and now you can see the high-tech quality solder job here. I could probably break this by just pushing it a little bit. I mean, really? Yeah. This is how it is. Oh, did I say about drain? The positive input voltage goes to all the drains of all the FETs. And of course they didn't want to add any thermal resistance to the hot field effect transistors. So what they have done is they connected the drain directly electrically as well as thermally to the heatsink. And that is not a problem, because the heatsink is just inside the case. But don't push or press on the case so the case go in and touch here, especially if you got 150 volts running here. You can see the distance here is not that much, and this is really thin and flimsy case, so you could easily push it in and touch the heatsink, and that means you have high voltage on your chassis. But it's a very good idea to do this because of thermal conductivity. So that way your FETS runs colder. So I think it is an okay way to do it. So this is how it looks when I solder stuff. Here's a little quiz. Can you see which one of them I soldered? Yeah. Let's try and understand a little bit how the manual works and what the manual says about the menu system. Previous clip I showed that this load goes into load on every time I turn it on, and that is every time I turn on mains power, the load go into active load state, and that is definitely not what I wanted to do. So what you do is you go to shift mode, that will be menu. And so now we are at the first page of the menu system. I will show you the first page from the manual, and be careful not to laugh so much. I think they wrote the manual in Chinese and then they use an auto translator, and they did not check the contents at all, because I've tried to highlight here some funny words. Nixie types, nixie displays. No, this is not a nixie display. This is a 7-segment LED display. Okay, and then they say a 4-bit display or a 5-bit display. No, it is how many characters we have on each line. And this model got 5 characters. So of course that will be the possible menu points. That will be the 5. Oh my God, that is a little bit funny. Okay, so this is the first one, okay? Now, look what we can do here. We can look at the A, that reveals the first point. If I go on this one that is blinking and I go down, see? Then I can edit information here on the address. And then this number 1 is also important. Then we go back to the blink and then we go to the right. So we are at B, configuration, C, battery modes, D, E, F. So that is the main entry points in the menu system. And this is what you need to understand first of all, right? Let's go back to A. So this is the system settings. We go down. We don't want to play around with address for the serial ports and all that kind of stuff. Not so interesting. 2 is a ball rate. So it's 9600. So this is the online mode and it's slave or. So here is the interesting. This is the memory mode where it will be able to remember the last menu point. And if your load was on or off, it will remember this to the last time or next time you power it up. That is what the manual say. However, this is wrong. The manual should say something about if you select on here, your load will always go on no matter what the last setting was. I mean, come on. So we go back here and then we go down and change this to offset. So now your load will go on. It will not go on. It will go off at the first power up. That is what we want. Oh man, my God, this is crazy. Why would anybody want this to go on? Anyway. And this is the sound. Is of course off if you enable. Oh yeah, I can show you how to enable stuff. So there's a sound and then you enable and you go back up. Oops. Sound. Go down. Enable and then you have to hit set. Now it is saved. We go up again. Down again. And then it is off. And this is sound. We go down to sound. We don't want sound. Set. Sound is now off. And we go out. So this is how the menu works. And of course, I really encourage you to read around in the manual to figure all this out in more detail. But that was just the basic. Since the meter here got a very fine resolution in all the readings, you can see a 1 millivolt resolution in the voltmeter. So you would of course expect it to be accurate. It is a little bit, it's only about 5 millivolts off. Hardly anything to complain about. I mean, who would care about that really? So just don't use the last digit to be honest. I mean, but you could software calibrate this thing. All you need is a very stable voltage supply that can give you exactly 10 volts, but you also need to make 80 volts. So at those 2 points you can store the correct voltages, and then it will read out much more accurately in the future. And so that is what I'm trying. So what I'm going to try and do for the last little experiment. So first I will write down exactly what it is reading and how much it is reading to low, and then I will compare it with another voltmeter I think is a little bit more accurate, but as you see it's only 5 millivolts off here, so this is not a lot. We could also try 80 volts and see how much is it off at 80 volt. Okay, so it's 50, 60 millivolts off. So it says 79.95 6 almost in a few seconds now, and then I go here. You see? So I think I can probably fix this if I try to do the calibration routine. There is another YouTube video that in great detail explains exactly how to perform the voltage calibration. So it's really a waste of bytes to repeat this, and he explained this super good. So please, if you're going to voltage calibrate it, just search for this number here and then how to do the voltage calibration. There's a fantastic YouTube video on that. So I was able to follow the calibration procedure, and that was quite easy. All you have to do is just go and watch that video. Definitely good. So look at that. I've changed a little bit on the input voltage and all that kind of stuff. So this is my input, and I think we are as close as we can possibly be. That was nice. So I think this concludes this load video for today. Thank you very much for watching, and bye bye.